All right, Unit 1. So let's look at some of the highlights of Unit 1. And the first one is I wanted to cover two terms. One is mass and the other is weight. Not to be confused. So mass is a measure of the amount of matter an object or substance contains, where weight is a really measure of how strong the gravitational field of pull is on an object. So the greater the gravitational pull on an object, the more it weighs. And they're related because an object that has a greater weight is going to have more mass. However, the weight of an object will change if you're going from one planet, for instance, to another planet. And if if the planet is bigger, the gravitational pull is stronger. Example, if you look at the moon and the Earth is much more massive than the moon. If an object has a weight of 16 pounds on the moon, it would have a weight of 100 pounds on the Earth. And the mass would be the same. It's not going to change. And that's why on here, what it is, I have this box here, okay? And what I'm saying here is that this box has the same mass as this box here. And the mass will not change, but the weight will. Again, because the gravitational pull is greater. And the greater the object. As a matter of fact, both these objects actually have gravitational pull. We do. Even our bodies do. It's just so small that it's not really something that we are able to detect. But the Earth, because it's so big, its gravitational pull is much greater than this box. Okay? So again, the mass of the object does not change if it is on the Earth or the Moon. And this is true because the Earth is much more massive than the Moon. Okay? Let's look at another term, kinetic energy. Kinetic energy is the energy of motion. And the amount of kinetic energy depends on the speed and the mass of the object. The greater the mass of a moving object, the more kinetic energy it has. And the greater the speed, the more kinetic energy the object has. So let's look at a car. Okay? We have a car. And let's take a look at two scenarios. I have a car here, and the car is sitting, right? But then the same car is actually moving. All right, that's our car. And if the car, when it is moving, all right, so this one is standing still, but this one is moving. Right, the mass doesn't change, but the kinetic energy will. This one, because it's not moving, it has no kinetic energy. But this car here, it is moving, so this has kinetic energy. And the faster the car moves, the more kinetic energy it has. Also, if I can increase the mass, so if I have people that go into the car and they sit in the seats, that adds more mass to the car. If the car is moving, by having people in there, it's going to cause it to have a more kinetic energy. So assuming the speed is the same. So if the car is going, let's say 50 miles an hour, the kinetic energy would be greater if you added 4 people in there. Potential energy. Now, potential energy is really energy that's stored. And probably the thing we're most familiar with is that kinetic energy is stored because of position. So for instance, if I have a hill and I have a boulder on the hill, up here at the top of that hill, this has the greatest amount of kinetic energy. All right? So this has the most kinetic energy. sorry, potential energy. Sorry, potential energy. But as this boulder, if it falls down, it rolls down the hill, its potential energies have become less and less. Here it has less than here, right? So if I say this is position one, position two, position three, and position four. Position one will have the greatest amount of potential energy, and then position two will have a little less. Position three will have less, and position four would have the least of those. And then when it comes to a rest at the bottom of the hill, it has lost quite a bit of its potential energy. That should be a 5. All right. So in position 5, it will have the least amount of potential energy. All right. So here. But also potential energy can be stored in chemical bonds. And that's an important one. And we'll see this. You see this when you look at an object that burns. When it burns, let's paper or wood. When the paper or wood burns, it releases heat and light. That heat and light is actually the energy released from chemical bonds that are broken. The food that we eat, let's say you eat a hamburger, right? So that hamburger will have energy in the form of calories, and those calories, that's a measure of the energy that's actually in the bonds, the potential energy of the bonds. And when we eat it, we will extract that energy and we can use it in the cellular level. So it plays an important part in providing energy for living things. Now, states of matter. So there's more than three there's more than 3 states of matter, but we focus on the 3 most common states of matter. So gas, liquid, and solid. So the first thing we should look at is the amount of kinetic energy. So matter in the gaseous state will have the most potential energy of the 3 common states of matter. And solids will have the least amount of kinetic energy. And then liquid is in between. So a matter in a gaseous state, the molecules are constantly moving. And they're also far apart. Where liquid, the molecules are very close together, but the molecules are still moving. Or if you look at a solid, the molecules are very close together, and they're not moving. They're vibrating, but they're not moving. And as matter moves between those different states of matter, it's going to lose or gain energy. If you go from a solid to a liquid, you're gaining kinetic energy. You have to heat it up. And then if I go from a liquid to a gas, I have to add more heat to it. I increase the kinetic energy. But then if I go back down, so if I go from a gas to a liquid, I condense it, I'm actually going to lose heat energy. And then if I go from a liquid to a solid, I lose more energy. We can see this, actually we can observe this. If you've ever gotten a steam burn is water in its vapor state condensing on your skin. And it releases a lot of energy. Why? Because gas has a lot of kinetic energy, a lot of energy. And then when it goes from a gas to a liquid, it loses energy. And we feel that as heat. And if you go from a liquid to a solid, so in other words, if you look at water, it freezes. It's going to lose energy. This is actually used by orange grove growers. So if you hear sometimes where if there's going to be a frost with if a farmer has orange groves, what they'll do is they'll spray water on it so it will freeze. When the water freezes, it goes from a liquid to a solid. It's actually going to release heat, and that heat can actually warm up the fruit a little bit and can help save it from being damaged. All right? And so that's why I drew these arrows on here. I was trying to show that as we go from a solid to a liquid to a gas, you're increasing the kinetic energy, you're increasing the temperature. But if you're going from a gas to a liquid to a solid, you're decreasing the amount of kinetic energy, you're decreasing the heat. Now, mixtures. If we look at mixtures, it's two or more substances that are combined. But each of the substances retains its properties since they are not chemically combined. That's different than a chemical reaction. So there's no chemical reaction occurring. The substance of a mixture or composed of can be separated by physical means, such as passing a mixture through a filter. If something, if it wasn't a mixture but it was a chemical reaction, you cannot separate them by physical means. Just a mixture. Now we have really two groups of mixtures. A homogeneous group. A homogeneous group is a mixture that has a uniform composition throughout the mixture. So in other words, no matter where you took a sample, no matter in a homogeneous mixture, no matter where you would look in the mixture, the composition would be exactly the same. So for example, if I dissolve salt in water, a solution is produced. And solution is an example of a homogeneous mixture. Homogeneous mixture. Solutions are made up of a solvent. So if we look at salt and water, water would be the solvent, and it's the dissolving agent, and a solute, and that's a substance that's dissolved in that water, for instance. So if I have a homogeneous mixture, let's pretend that this is water, and I have a substance dissolved in it produces a solution. What I would see is that the composition, I'm trying to make it as even as I can, but the composition throughout that liquid would be the same. Just like if I had again a saltwater solution, all the salt water, if it's mixed and you have mixed together and you have a homogeneous mixture, it's all going to be the same concentration of salt. It's going to taste the same. And a heterogeneous group. Where a heterogeneous mixture, the composition is not uniform. Cookie batter is an example of a heterogeneous mixture. I've even alphabet soup, if you think of it, it's a heterogeneous mixture. The composition changes from one location in the mixture to another. So if you look at a cookie dough, right, you take some of the dough out, you can have more, the composition. Let's say that the cookie dough had chocolate chips in it. If I take different samples of that cookie dough, you're probably going to have different amounts of chocolate chip in it. Why? Because it's a heterogeneous mixture. If it was a homogeneous mixture, it would be the same, exactly the same throughout. And cookie dough is not going to be homogeneous. It has to be heterogeneous. Density. Density to measure the amount of matter found within a defined volume of a substance. And so, example, if I have air and I have water, we know just from our daily experience that air is less dense than water. But what does that mean? Let's say I have a container, a cube, right? Two cubes. One cube, pretend they're the same size. One cube has water in it, and one cube has air in it. And I took those cubes, and I put them on a scale. All right, put the cube on here. Let's say this cube had air in it, and then I measured again. I take the scale, and I put the cube on there. Again, the cubes are the same size, and this has water in it. And the one with water is going to have a greater density. It's going to have more mass, even though it's the same size. What that means is that in that given space, there's more matter in water than there is air. And if you remember, when you go from a liquid to a gas, the molecules are further apart. So it kind of makes sense. Air we know is a gas. The molecules are further apart. Water, which is in its liquid state, the molecules are very close together. So there's more matter within that same cube compared to the air. And we can see this mathematically. So density equals mass divided by volume. So I can figure it. I can figure the density of anything if I know the mass and the volume of it. So for instance, let's say that I have an object that has a mass of 4 grams. And the volume is 1 centimeter cubed. That object is going to have a density of 4 grams per centimeter cubed. Knowing that, if I double the volume of that object, let's say I have an object that's 2 centimeters cubed. Let's say it's the same object. So this object has a density of 4 grams per cubic centimeter. If I know the density, I can predict that this object is going to have a mass of 8 grams, because I know every cubic centimeter has a mass of 4 grams. So if I double the size, I'm going to double the mass. And oftentimes you'll see terms when we talk about water, the specific gravity of something. That's really referring to the relative density of something. So if so for example, if something has a specific gravity of 1 compared to water, it says that the object has the same density of water. An object that has a density less than 1 compared to water will float in water. And something that has a density, specific gravity greater than 1 will sink in water. Okay? So those are some of the important terms from the Unit 1 notes. Thank you.